This is the second part of the two brief lectures on cyclic voltammetry. In the previous lecture, we had introduced what is cyclic voltammetry and argued qualitatively on how to get the current in response to the voltage scan. So what makes the analysis of cyclic voltammetry quite complicated are the effects of mass transfer. We derive this under certain limiting condition. However, the real system has significant complexity due to mass transfer. So if we try to use the most general equation, that is, the most general equation have three components to the flux, right? There is this migration flux, convective flux, and diffusive flux. The migration flux can be completely suppressed by using supporting electrolyte, or more or less completely suppressed by supporting electrolyte. And the convective flux is also negligible because we have quiescent or a stagnant electrolyte. There's no explicit convection. And there might be natural convection, but that is in general small in the regimes which we are considering. So the effects of migration and convection can be made negligible, but just solving for the diffusive fluxes itself is complex. We looked at how to solve this particular equation involving diffusive flux in a particular limiting scenario. What was the scenario? Few lectures ago, we looked at what is the current response when there's a sudden change in potential. Okay, so even that scenario is fairly complex, but we were able to get analytical solution to that particular experimental system. But here, our voltage scan is much more complex, making the entire system fairly complex. So most of the realistic simulation of cyclic voltammetry is done using complex numerical procedures, which is beyond the scope of these set of lectures. However, we can glean a lot of insight just from some qualitative analysis, but it's important for you to understand what are the underlying equations that go into the complete qualitative analysis. So this is a PDE, which is first order in time, and second order in spatial derivatives. So we need three conditions. So because the potential at the working electrode is provided, that's what we are imposing. So that provides us with one condition. The concentration in the bulk, that is far away from the electrode-electrolyte interface, that is the concentration at infinity, is also known. That provides another boundary condition. And the initial condition is also known to you. That is what is the concentration profile at t equal to 0 is also known to you. That will provide the initial condition. All the conditions for solving the PDE is known. So once you have these conditions, you can solve it, let's say, numerically and get the relevant concentrations. Okay, so once the concentration of CR and CO is available to you, you can use that to calculate the exchange current density. And you can use the Butler-Warmer equation, assuming you know alpha A and alpha C. We may be using, most of the time we are using this value of 0.5 in our analysis. So you can use that, and there is also the capacitive contribution to give the overall contribution to the current. All these things, we can state the equation simply, but to actually implement it for a real system is not that simple at all. So in most cases, we resort to either qualitative analysis or a semi-qualitative analysis only in this case of cyclic voltammetry. So the essence of the reversible system is that once you impose the potential at the working electrode, we can fix the concentration of the redox couple just based on the potential. Okay, so this gives us a considerable simplification. So this is the case of reversible kinetics. If the activation barriers for oxidation and reduction for electron transfer involved in oxidation and reduction is very less, we can assume reversible kinetics. This significantly simplifies the problem, and we sketched this kind of a curve in the previous lecture. So why is there a peak? The peak is because of convolution of two effects. As we go in the anodic direction, the thermodynamic driving force for oxidation increases, right? So what do you mean by that? R will get oxidized to O. So as we move in the anodic direction, the thermodynamic driving force increases. So beyond a particular onset potential, the oxidation starts occurring. Even though the thermodynamic driving force increases as we go in the anodic direction, the amount of species available to you that can be oxidized keeps decreasing. Okay, so the convolution of these two factors gives rise to an anodic peak. Likewise, we can argue in the cathodic direction. So going from a completely qualitative analysis to a slightly more quantitative analysis gives an important result, which is used in cyclic voltammetry, experimental analysis of cyclic voltammetry. So what is this result? The difference between the peak voltages, that is between this, the voltage of this peak and the voltage of this peak, cathodic and anodic peak, this difference has to be this quantity, where N is the number of electron transfer involved in your electrochemical system. Okay, in this case, N is 1, but this result is quite general. And for a completely reversible kinetics, this result is valid. So how do we use this result? So supposing you know your system is reversible, but you do not know the value of N. Okay, so using this relationship, you can get the value of N from this relationship, or the other way around. Supposing you know the value of N for your particular system under consideration, and you do the experiment and you compute delta EP, okay, the difference between the peak potentials, and how close it is to this number is a measure of how reversible your system is. So if the delta EP is close to this value, then you can say your system is more or less reversible. The further away you are from this value, the system is less and less reversible. That is the utility of this relationship. So you can also understand certain other aspects when you change certain parameters. Typically, how do you do these experiments is that you do these experiments at different scan rates. That is, you first, let's say, do it at 20 millivolts per second, 40 millivolts per second, 80 millivolts per second. Okay, so this gives you the response of current to different scan rates. So what do you observe here? As you increase the scan rate, your peak current increases. Okay, so there is a way to, again, qualitatively interpret this data. So how do you think about this? As you decrease the scan rate, let's say you go from, let's say, you do the scan at 20 millivolts per second. If the scan rate is lower, the mass transfer boundary layer is also larger. Okay, so the mass transfer boundary layer penetrates to a greater extent, because of which the concentration gradient is also lesser. If the concentration gradient is lesser, the transport of the species from the bulk to the electrode surface or from the electrode surface to the bulk is also lesser. So the thermodynamic driving force remains the same in all these three cases. Okay, so even though the thermodynamic driving force for oxidation or reduction remains the same in all these three cases, the amount of active species present is very different in these three cases. The active species that can be oxidized is least in this case because of lesser concentration gradient and greater penetration of mass transfer boundary layer, the greater thickness of mass transfer boundary layer. So the peak is the current density at the peak potential is highest for 80 millivolts per second because there is a steeper concentration gradient in this case. So that is one way to interpret this behavior. But another general feature you should be able to know is that when you go from near reversible system to more and more irreversible system, what happens is that the difference in peak potentials moves away from this value. All right. So that is a measure of irreversibility. So as you go from near reversible system to more irreversible system, what do we mean by more irreversible system? The activation energy for electron transfer keeps increasing. Okay. So making the system more and more irreversible. So the peak potential, the difference between peak potential, delta E subscript P, becomes further and further away from what you have derived for a near reversible system. So this thing is valid only for a near reversible system, so not for an irreversible system. So things can get quite complicated. So here we are showing three different cases. There is this reversible case, which is indicated by the black curve. We have discussed this sufficiently in the last two lectures. So the brownish curve is a quasi-reversible system. That is, it is not as reversible as this system, but still there is some reasonable reversibility. So going from reversible to quasi-reversible, what we see is the delta EP is different from what you have derived for a reversible system. And you can also have a completely irreversible system. What do we mean by that? Supposing you have oxidized a species. Okay, so there is the reduced species has been oxidized to O. Okay, so you do observe a peak potential for the oxidation current. However, when you go in the cathodic direction, it is no longer possible to reduce the species O. Okay, so once the species O has been formed, the backward reaction, O changing to R or O getting reduced to R, is suppressed. That activation barrier for the reduction step is quite high. So that step is irreversible. So you may see lesser and lesser value of current density for the cathode peak. Okay, so sometimes you may not even see a cathodic peak at all. You may only see the anodic peak, but there might not be a cathodic peak. So the overall theme is that you should be able to understand how to interpret cyclic voltammetry, at least in a qualitative manner. Okay, so in the absence of numerical simulation of cyclic voltammetry, it may not be possible to get a quantitative understanding for your system. So at least for within the scope of these lectures, my expectation is that you should be able to get a qualitative interpretation, because cyclic voltammetry is probably the first default experiment you begin to do when you look at your system. So it's a very important technique. So at least you should have some exposure to this technique. In the next lecture, we will move to another important topic of great utility, which is that of stripping analysis. We will do that in the next lecture.